everyone! Welcome to part 6 of chapter 17. This is our last lecture on chapter 17. Today we are going to talk about precipitation and how to make certain ions precipitate. We're going to look at selective precipitation, which means precipitating one ion instead of, multiple that may be in solution. And then we're going to use that to talk a little bit about qualitative analysis. And we will deal a lot more with qualitative analysis in lab. So this will serve as just a really brief introduction to what it is. And then, like I said, we're going to spend a lot of time in lab covering qualitative analysis. So let's get started. So precipitation, right? Precipitation occurs when we pour together two aqueous solutions. Okay, so if we pour together two aqueous solutions and a solid forms, that is the formation of a precipitate. Okay, and this will happen when the concentration of the ions in the solutions exceed the solubility of the ionic compound. Okay, if the molarity of those solutions is greater than the molarity that we should be able to have for that KSP, then that will cause a solid to form in the solution. Okay, so this will be for insoluble, or right, we've talked about what insoluble really means. This will be for insoluble solids. So we're always going to compare the reaction quotient Q to our KSP. And if you'll recall from when we were doing equilibrium really early on, right, we said Q was when we weren't sure if it was at equilibrium. It could be, right, but Q was just our concentrations that we had at any given point in time. So the same will be true here. We'll calculate Q, but which will be calculated the exact same way we calculate KSP. So essentially we're calculating KSP, right, but we're going to just call it Q or QSP, and we'll compare that to KSP. If Q is equal to KSP, then our solution is saturated, and it will usually not cause precipitation. Okay, this is kind of like when Q equals KSP, that would be the point at which precipitation is just about to start. If Q is less than KSP, then it's unsaturated, so no precipitation. But as soon as Q is greater than KSP, right, that's what we were talking about here, when the concentration of the ions exceed the solubility of the compound, then it would be oversaturated essentially. We'd have too much of our ions, and our salt will precipitate. There are some instances where we can have Q that's greater than KSP and it won't precipitate, but these are very special instances, and these are called supersaturated solutions. So if you go back onto Canvas and look in the module for chapter 17, I've actually posted a short video, it's 3 minutes, of a supersaturated solution of sodium acetate, which we'll talk about on the next slide. But it's really neat. It looks totally clear, but as soon as you add a crystal, or as soon as you disturb it, right, in this case they were pouring it, then it will cause it to precipitate out. It's really neat. If you've ever made rock candy, that is an application of supersaturated solutions. So it's really neat. So just to sum up on this slide, if we have, right, Q is going to be essentially our KSP at any given point in time, and we're going to compare that to our KSP. If it's equal to KSP, our precipitation is just about to occur. Okay, if it's less than KSP, it's going to not be a precipitate, and if it's greater than KSP, we will have a precipitate. Okay, so again, if Q is greater than KSP, then we will have a precipitate start to form. So that's what's happening here. We had silver nitrate and we added sodium chromate, and we're getting this, kind of red colored silver chromate. That would be our precipitate, because if we think about this, right, silver nitrate, anything with nitrates are always going to be soluble, and we have sodium chromate, anything with sodium always going to be soluble. So these are both aqueous solutions that we've added together, and when we add them together, we're getting the formation of silver chromate, which is our solid, so a precipitate has formed. The stuff on the right is what I was talking about with the sodium acetate. So this is a supersaturated solution of sodium acetate. And again, it looks totally clear. But as soon as you add just one teeny tiny little crystal of sodium acetate, right, of solid sodium acetate, that provides a nucleation point. And so once it hits the surface, it will start to grow these cool crystals. And again, like I said, I've posted a video. I think it's really interesting. It's fun to watch, and it's only 3 minutes, so I would check it out. All right, let's go ahead and do a little bit of calculations associated with precipitation. So this says, will a precipitate form when we mix lead nitrate with sodium bromide if the concentrations after mixing are there? Okay, so again, we're always going to want the concentrations after mixing, right? Not the concentrations of the solutions alone, but the concentrations of the solutions together. So that's what's been given here. So we have our KSP value, right? We're going to form lead bromide. So we have our KSP value there. So we'll go ahead and we will calculate QSP and compare that to KSP to determine whether or not a precipitate will form. Okay, so here's our reaction. Whenever we're doing KSPs, remember that we're always writing the equation for the dissociation of our solid. So our solid is always going to go on the left, and our aqueous ions will go on the right. So when we write our KSP value, or our KSP expression, it's going to be KSP is equal to lead, right, and it doesn't have a coefficient, times our bromide ion squared. So our QSP is going to be the exact same thing, right? KSP and QSP are the same. This just isn't at equilibrium yet. So we'll plug our values in for lead and for our bromide, okay? And then we can go ahead and calculate our QSP. So again, we're going to compare that to our KSP here. And we'll see that Q is less than KSP, so precipitation will not occur because our concentrations are still small enough that they don't cause our solid to fall out of solution. Okay, we haven't reached that maximum concentration that can be held in solution. Let's try another one. So if 1 gram of sodium chromate is added to 225 milliliters of 0.15 molar silver nitrate, will a precipitate form? Okay, so again, this is like that picture we had. We had silver, we had chromate, so we're forming silver chromate here. So we have a molarity of our silver nitrate, and we are adding a solid, right? We're adding solid sodium chromate. So we need to find the molarity of our sodium chromate in order to be able to plug it into our KSP expression. So let's go ahead and give this a go. So we have that there. There's our dissociation reaction for our silver chromate. Okay, and we can determine our initial concentration of our ions. So we'll take our 1 gram of our sodium chromate and figure out the concentration there. So we'll divide by the molar mass to get moles of sodium chromate, and then we'll divide by that volume in order to get our molarity here. Okay, it's important to note that I calculated the moles of sodium chromate. That's going to be the same as the moles of chromate because they're on a 1-to-1 ratio. If I had needed the moles of sodium, right, which I never will because, you know, sodium's always going to be aqueous, but let's say it was, you know, calcium or aluminum or something, right, something else. You need to make sure that your moles are, you know, are in a 1-to-1 ratio, or you need to be multiplying by a factor. So if this was sodium, I would need to multiply that number of moles by 2 before calculating the molarity. So then we'll divide by the total volume, and we'll get the concentration of our chromate ion in solution. We already had the concentration of our silver that was given to us in the problem. So now we can go ahead and plug this in to our QSP. So we'll plug them in there and calculate that. And again, we're going to go ahead and compare that to our KSP. Now, Q is much greater than KSP, like a lot greater, right? So this is definitely going to form a precipitate in this case. All right, here's another one. So this is the same problem, but now that I know that it forms a precipitate, I want to know what mass of the precipitate will form. So how much precipitate will we get? And I want to know what is the molarity of the ions left in solution after the reaction occurs. So we'll do one and then we'll do the other. So the way that we are going to solve this is we are going to do a reaction ice table, right? Because the sodium chromate is going to react with the silver nitrate to form our solid, okay? So when we do a reaction ice table, remember that we need to do these ice tables in moles. So the first thing we need to go through and do is calculate the number of moles of each substance. So we have our moles of silver by multiplying our molarity times our liters, and then we can find our moles of chromate by just dividing by the molar mass, okay? And then we can go ahead and plug that into an ice table. I'm going to go ahead and flip this reaction around because we are forming silver chromate instead of writing the reaction for it dissociating in water. Okay, because I like to think of, okay, the silver and the chromate are going to react. They're going to form silver chromate. You can totally leave it the way it is above. It just makes more logical sense in my head to flip it around to show the reaction. Okay, so here's our ice table. So I'll put our moles of each one, and we don't have any silver chromate to start with, and then we'll go ahead and fill in our X values. So again, remember that when we have coefficients here, we need to carry them down with our X's, just so that we are having stoichiometric amounts of everything. So then we'll go ahead and we'll figure out our limiting reagent. You could probably guess that it's going to be chromate in this case because it's quite a bit smaller than the silver, but it's always good to double check. So remember, the way that we do that is we set, both of these equal to 0. So we'll have 0.34 minus 2x, we'll set that equal to 0 and then solve for x. And then we'll put 0.00617 minus x equal to 0 and we'll solve for x. So our chromate really was limiting, but it's always good to go ahead and double check. So then we can plug that value in for x and then add them straight down to get our equilibrium concentrations and figure out how many moles of our solid has formed. So now that we know how many moles of our solid we have, we can go ahead and use the molar mass and convert that to grams. Okay, so that's the first question, what mass of the precipitate will form. So now we need to figure out what is the molarity of each ion left in solution. So right now, if you look at our E line that I've put up there, we have 0.022 moles of silver and 0 moles of chromate. Well, remember, this is an equilibrium. So there's not really 0 moles of chromate, right? There's a little bit. So we need to do an equilibrium ice table to figure out, okay, well, how much chromate is really in solution? Because it's not 0. So I'm going to go ahead and calculate my molarity of our silver so that we can do this equilibrium ice table, because we do equilibrium ice tables in molarity. Okay, and it doesn't matter, right? I'm not going to do that for this because that's a solid, so we don't calculate molarities for solids. They don't show up in our equilibrium ice tables. So I'm going to go ahead and flip this reaction back around to show the dissociation of my silver chromate back toward my chromate. Okay, again, you could have left it the other way this entire time. It just helps me think about what's actually happening in our reaction. So here's our ice table. I'm just going to cross out our silver chromate because it's a solid and it doesn't matter anymore. And we don't have any of our chromate, but we'll use our new concentration of our silver in our ice table. So then we're going to dissociate towards our product, so plus 2s and plus s, and then we'll add that straight down. So then we can plug that into our KSP expression. So we have KSP is silver squared times chromate, again, because of this 2 in front of silver. So we can plug our values in from our E line, and we get that there. We're going to go ahead and say that our change in concentration is negligible because we've got times 10 to the minus 12 up here. So it's really not going to make a difference in our calculations. So we'll go ahead and get rid of that. And then we can go ahead and solve for our S value. So once we get S, right, S is going to be our concentration of our chromate. Okay, so that's this, and then I'll talk about silver in a second, but that's our concentration of our chromate, so we're done there. Again, it was really, really small, so it wasn't 0, but it was really, really small. And then silver, we have 0.098, plus 2 times that value, and again, that really was negligible. It didn't change our concentration at all. So there's our concentration of our ions in solution, and we found our mass of our precipitate. All right, one more for these. So what is the minimum concentration of calcium nitrate that will precipitate calcium hydroxide from 0.0175 molar sodium hydroxide? So this is a really useful problem in the lab because we're going to do these selective precipitations, right? Where we want certain things to precipitate out, but not others. So a lot of times we'll want the minimum amount that we can add in order to cause the precipitation because we can separate some things based on their differences in KSP values, right? So if say calcium hydroxide is less soluble than something else, right? We can add just a little bit of our sodium hydroxide or a little bit of our calcium from the calcium nitrate, and cause that solid to precipitate without causing whatever else is in there to precipitate. Okay, so this is leading into that. So we want to know the minimum concentration. And the way that we do this is we say, here we go, precipitation will begin to occur when QSP is equal to KSP. Okay, and that's what I was talking about in the previous slide. When we have QSP equal to KSP, that is when it is just starting to precipitate. Okay, and so that's going to be the key for solving this problem. So we have our dissociation equation there. So it dissociates into calcium and 2 hydroxides. So we can write a KSP expression, which is going to be the same as our Q expression, or QSP. Right? So we have calcium times our hydroxide squared because there's a 2 in front of hydroxide. So once we've got that, and we've got our KSP value here, right? Because Q is going to be equal to KSP when precipitation starts. And now we can go ahead and plug in this value for the concentration of our hydroxide in order to solve for the concentration of our calcium. So when we plug that in, right, we can go ahead and solve for our concentration of our calcium. Okay, so this is a pretty straightforward problem, but it's really useful when we are doing these selective precipitation problems. Okay, so selective precipitation. We are going to say that we have a solution that contains several different cations. And the way that we are going to separate them is we are going to add reagents that form insoluble salts with one of the ions or some more of the ions, but they'll have different KSP values. So the whole point of the selective precipitation is that we want to precipitate one specific ion and not any of the others. Okay, we want to be able to separate all of our cations from each other. And the way that this will play out in lab is we will separate all of our cations and identify them. It's going to be really fun. You're going to like it. Qualitative analysis, I think, is like a puzzle. And it's one of the reasons that I actually changed my major to chemistry partway through college is because I had a great time in qualitative analysis. But the whole foundation of qualitative analysis relies on us understanding selective precipitation. So precipitating out one ion, but not any of the others. Okay, and like I said, if we have a successful reagent that maybe combines with more than one cation, like hydroxide's really common, right? We form a lot of insoluble hydroxides, like calcium hydroxide, magnesium hydroxide. We've got aluminum hydroxide, iron hydroxide, zinc hydroxide, right? So if we add hydroxide, all of those ions are going to precipitate out. Well, we can cause them to not all precipitate out at the same time by only adding small amounts of hydroxide so that only one or maybe 2 of them precipitate out and not all of them. Okay, and this will be if their KSP values are significantly different. So here's a problem. So it says the solution's made by mixing lead nitrate with silver nitrate. So they both have compounds have a concentration of 0.0010 molar. Okay, so essentially what's happening is we have lead and we have silver, and then we're going to add sodium chloride, and that will cause a precipitation of both silver chloride and lead chloride. So we want to add just enough, chloride to precipitate one, but not the other, is usually how this would work. In this particular problem, I want to know what is the silver concentration when the lead just begins to precipitate. Okay, if we look at these, if we look at our KSPs, our silver chloride has a smaller KSP, so that would lead us to believe that silver chloride would precipitate first over the lead chloride. We actually can't directly compare these because our silver chloride breaks into 2 pieces and our lead chloride breaks into 3. So that might not always be true, but in this case, I will tell you our silver chloride will precipitate first and our lead chloride will precipitate after. Okay, so this is asking what is the silver concentration essentially left in solution when the lead just starts to precipitate? Because the silver will start to precipitate out, so our concentration of silver will steadily decrease until we get to the point where then the lead starts to precipitate. Okay, so the way that we're going to do this is we are going to calculate how much chloride it will take to precipitate out the silver. Okay, so in order to do that, we need our KSP, KSP value up here, and our dissociation equation. So then we can write our KSP, which is going to be the same as our Q, right? Because Q will equal KSP when things just start to precipitate. And then we'll use our concentration of our silver in this reaction to solve for our concentration of our chloride. So if we rearrange, we can figure out the concentration of our chloride when silver just starts to precipitate. So that's a really small concentration. So this is just even a teeny tiny bit of chloride will cause the silver chloride to come crashing out of solution, right? 1.8 times 10 to the minus 7 molar, right? We've never worked with anything that small. So this shows us that silver chloride is very insoluble. So now we can do the same thing and figure out how much chloride it will take to precipitate out the lead. So we'll write our dissociation equation, and then we'll go ahead and calculate our Q, which is our KSP, and we'll plug in our value for lead. So then we can keep rearranging. We'll solve for our concentration of our chloride, and as you can see, it takes a much greater molarity of our chloride to cause precipitation of our lead, right? I mean, look at these. That's crazy, right? Silver chloride, very insoluble, will precipitate out very easily, whereas the lead, we need a fairly high molarity of our chloride in order to cause precipitation. Okay, so back to the actual problem. So I want to know, what is the silver chloride or silver concentration when the lead just starts to precipitate? So the way we're going to do this is we're going to use this concentration of our chloride, right? When the lead just starts to precipitate, that'll be our concentration of our chloride, and we can use that to calculate our concentration of our silver. Okay, so we have the same reaction, and we've got our same values here. So we'll plug that value in for our chloride, and we can solve for the concentration of our silver. So as you can see, right, we started with a concentration of 0.0010 molar silver, and when the lead just starts to precipitate, it's much lower. So that means that a lot of our silver has already precipitated before the lead has. So we can almost completely separate these, right? Because we'll have very little silver left in solution when the lead starts to precipitate. So it's kind of neat. Okay, so the selective precipitation is going to be really useful in qualitative analysis. And qualitative analysis is an analytical scheme that utilizes selective precipitation to identify ions present in a solution, okay? So we're going to, again, add certain reagents to cause some solids to precipitate, but not others, and we're going to use that to separate and identify our cations. Okay, so in lab, you're actually going to be handed a sample, and it's going to be a totally aqueous solution, right? There's not going to be any solid in it. And your goal will be to tell me what's in your solution. And the way that you're going to do that is this whole selective precipitation. Maybe I add some hydrochloric acid. Does a precipitate form? No, then it's not forming a chloride in acidic solutions. Well, maybe I'll add some hydroxide, right? Will a hydroxide form? And you'll go through this whole process of elimination to figure out what is in your test tube. Like I said, I think this is really fun. This is one of the reasons I love teaching Chem 2, is because I absolutely love qualitative analysis. Okay, and then the name qualitative analysis is we're just trying to figure out what it is, right? Quantitative analysis is most of what we do in chemistry, where we're asking how much it is, right? How much product did you get? What percent yield did you get, right? We're always trying to assign numbers to things in chemistry. But qualitative analysis is just, what is it? Is it silver? Is it lead? Is it copper? What did you get, right? That's qualitative analysis. So here's kind of just a general scheme of things, right? So say in the beginning you have a mixture of your cations A, B, and C. And you would add something, it doesn't matter what it is for right now, but you would add something, and that would cause, say, cation A to form a precipitate. And then we could decant off the liquid, right? We'll pour off the liquid. We'll keep our solid in this test tube because we can do what's called confirmation tests to make sure that that's really what it is. But we can pour off the liquid, and now we have, no more solid left. And then we'll add another precipitating agent, okay? And that will, bond with one of them and cause an insoluble solid. And again, we'll save that test tube and we'll run some confirmation tests. But then we can decant off the liquid, and then we have cation A, and we can run, a confirmation test there to make sure that we really do have what we have. Okay, so it's really neat. Oh, actually, this should say C. Sorry, not my graphic. Right, but in this way, we separated cation A, B, and C in this whole qualitative analysis scheme. And like I said, we'll run confirmation tests that say, yes, it turned yellow. That means I have this. No, it didn't do that. Maybe I have something else. So here is kind of a really general qualitative analysis scheme. Okay, I do not want you to memorize this in any way, shape, or form. We will use one that's kind of similar to this in lab, but it will be different. So please do not spend any time memorizing this. I just want to talk through it so you get kind of the idea of how it works. So when we add, say, 6 molar hydrochloric acid, okay, and sorry, let's start at the beginning. This is all of the things we're starting with in our test tube. It's a really, really big test tube apparently, right? And we have all of this stuff in there. And we're going to add 6 molar hydrochloric acid. So anything that forms an insoluble chloride in an acidic solution will precipitate out, and that will fall to the bottom, like we had in that last graphic. That will fall to the bottom as our solid. Okay, and we'll take that, and then we can go through different processes and separate these 3 even further. Okay, we'll decant off the liquid, and all of the liquid will go this way. Okay, so this side was our solid, and this side is, what's in the liquid. Okay, this is called our supernatant, which is a much fancier word for liquid. So then all of our remaining cations, in this case, they're going to add dihydrogen sulfide and hydrochloric acid. Okay, and so some of those will make acid insoluble sulfides, right? Because we added acid here. So all of these are, insoluble sulfides in acidic solution. And then we can add a hydroxide, right? And we can up the pH to 8, and then we can separate all of the sulfides that are insoluble in basic solution, but it will also allow us to separate out all of the hydroxides as well. Okay, and then whatever else is left, we can add this guy, and then we can separate things as insoluble phosphates. Okay, and then some things will never form a solid, like sodium, potassium, and ammonia, right? So they will never form a solid. So you might be thinking, well, how am I ever going to know if they're in there, right? They're not going to form a precipitate, so they're just going to float around in solution. They don't even color the solution, so how would I know that they're in there? Well, for these, we can do a flame test, and we can look at what color the flame turns in order to identify the ions. Like sodium turns really pretty red, potassium turns purple, right? And so we can do that to identify these ions. Okay, so this is just going to talk through it in a little more detail, but again, don't spend a lot of time memorizing these. You're going to learn more about them in lab. Okay, these group 1 cations, remember, in the very first step, we added 6 molar hydrochloric acid. So all of these will form compounds with chloride that are insoluble in water as long as the concentration is large enough. Remember, we were talking about lead chloride a little bit earlier, and I said that we needed a ton of that chloride in order to precipitate out the lead. So we are typically going to add an excess of most of these reagents. So when we added hydrochloric acid, we're going to add in a ton of hydrochloric acid to make sure anything that's going to precipitate with hydrochloric acid will. Okay, so we're not trying to get it to just precipitate. We're trying to get it to really, really, really crash out of solution so that we can separate it, because we don't want any of this lead or silver or mercury still in our solution with everything else, because again, the goal is to try and separate everything. The second group were the cations that formed sulfides in acidic solution. Okay, so then when we add this, right, we'll form all of these different sulfides, okay, at low pH. And then we can add hydroxide, and we can get all of the sulfides that are insoluble in basic solution to crash out, as well as some of these hydroxides, right? It's worth noting that if you'll recall from when we were talking about complex ions, AlOH4- is a complex ion. So if we add some base, right, if we add some hydroxide, then it will form AlOH3, which is insoluble. But if we add too much hydroxide, we can actually dissolve this, this solid back up as this, right, which is soluble. Okay, so this is where we have to be careful. Whereas I said the chloride, right, just add a bunch of chloride because you want everything to precipitate out. This, it might be useful to add small amounts of hydroxide because you don't want things to precipitate, or, you know, if something's going to precipitate, you don't want it to dissolve again. So aluminum's a little bit tricky sometimes. But all of these are going to be insoluble in water at high pH. That's why I think it's specified a pH of 8, so that you can make sure that hydroxides stay as hydroxides and don't turn into complex ions. And then we have group 4 cations. These are going to form insoluble compounds with phosphate at high pH, so in basic solutions, right, because we had just added a bunch of hydroxide. And then the group 5 cations. So like I said, these ones are the ones that are always going to be soluble, and the only way that we can identify them is by a flame test, which I think is really fun. I always hoped that I would have some of these in my qualitative analysis so that I could light it on fire because, you know, what's the point of chemistry if you're not going to light things on fire, right? Anyway, so this is qualitative analysis, this whole separating and identifying different cations. I think you guys are really going to have a good time with this. And so it's coming up in lab. So this is something to look forward to. And that's the end of today's slides. So we covered precipitation, right? How to get something to precipitate out. We did some work with the calculations on that. When Q is equal to KSP, that's when our precipitation starts to occur. If Q is greater than KSP, that will form a precipitate. And if Q is less than KSP, then no precipitation will occur. We then talked about selective precipitation, right? Precipitating out one ion, but not others. And again, this is usually by adding either small amounts of our reagent, which cause something to precipitate, but not others. So this would be if they both form, say, chlorides or hydroxides, right? We would want to, add just enough to precipitate one, but not enough that it precipitates the other one. Or you can just simply add different reagents, and then you don't have to worry about that problem. And then we talked a little bit about qualitative analysis and how that is coming up in lab, and that's separating those cations based on the insoluble solids that they form with different reagents. So this is the end of chapter 17. Chapter 17 has been a ton of informations, right? This started way back when we started buffers, and we went through titrations, right? We've done a ton of work in chapter 17. So make sure that you are really, really working hard to nail down all of these different calculations. There's a lot of them, right? As always, if you have any questions or you're confused about something, please reach out to me and ask questions. I love to talk about chemistry, right? That's why I became a chemistry professor. So please make sure to send me questions if you have them. Chapter 17, like I said, it's a ton of work, but it's all leading up to qualitative analysis, which I think is a ton of fun. So make sure you're getting the information you need and keep working hard. Otherwise, I will talk to you guys next time.